Thanks to the organizers for squeezing me into the schedule at the very last minute. I'm here for the whole entire semester, so I kind of am one of these spoiled people who get to hang out and see all these workshops come through. So I kind of had to decide a little bit on very short notice what to do and what to kind of do in order to make the best use of your time on a Wednesday afternoon after a long day of talks. So I hope I found an entertaining way of doing this. I have to say though that I already gave you 2 talks in the tutorials that were more about the work that I do on a regular basis that relates deep neural networks and differential equations. So those got recorded, so clearly they are out of question for now, because you can go back into the IPAM website. They will do a fabulous job recording those. And so today I want to do a few things, and I chose a few case studies. And I'm trying to wear my hat as a numerical analyst who is exploring this big area of deep learning and asking himself, like, okay, what is there to do? What kind of insight can I bring into deep learning? And what has already been done and what is actually already in good shape? So the idea is, this is still this double clicking here with this guy. Okay, that I will talk a little bit about some background to set some context, what is deep learning, and set a little bit of my notation. And then I have like 4 case studies. So these were basically numerical examples. So I'll only do numerical examples today. No heavy math. That's and there's even one thing that is moving on the slides. And I will do a few things on the blackboards if there are some other things. And I'm really looking forward to a dialogue with you guys in terms of a discussion. So I don't have too many examples, but we can really discuss them in a lot of detail, and I hope they are educational for you. So one reverts or involves something that some learning applications really rely on. That is invertibility. It's a buzzword. If you have, say, a deep neural network and it embeds some features into a latent space, you want to be able to go to that space, and you will also want to be able to go backward. Not always important, but sometimes it is. So I want to give one thing what that means for the numerics to make that happen. Then if you work in differential equations, so I don't know how many people have heard about something called neural ODEs. I guess everyone. Okay, that's very good. We like friendly competition. So there is an argument of if you have a differential equation, what kind of time integrator should I pick? And typically the rumor on the street is that I always go with the one that gives me the highest order of accuracy. So I want to just make one classical point that not always is the best idea. And then sometimes you want to, for example, be conservative in the sense, not politically, but in the sense that you want to make sure that your discrete scheme carries over some of the things that you like about your solution. Then there's a big debate about when you work with differential equations and you want to optimize them. At some point you need to discretize, and there's a big argument when you should do that, in the beginning or in the end. So I'll have one example actually working a little bit with the neural ODEs. And then a standard question in numerical analysis is we like to talk about the conditioning of a problem. There I just will show you a very simple example how ill-conditioned and ill-posed some of these learning problems can be in very innocent settings. So that's kind of the idea. So these case studies are really case studies. So they don't really build up on each other. They're more or less independent. We can spend as much time on any of them as you like. And like a key question is, what can numerical analysis do in the age of ML? There are it seems that everything is going to change, and we are looking for a new place. Okay, so deep learning. Typically you look at these pictures. People who were here in the tutorials know that I don't understand these pictures very well, so I replace them typically with some equations. So and I typically like matrix vector notations. So basically, these y's are going to be my features. J denotes a layer. And this is like a feed-forward neural network with a single layer perceptron. With a fine transformation, the kj and the bj are parameters or weights that you want to learn. And this is sigma is an activation function. And then there's a whole zoo of what you can do and what you can build. And all the information that you have in the picture is encoded in these operations, actually. So if you have a picture here where you have arrows between all these circles, that is called a fully connected layer, which basically means that the kj is a fair game to have entries all over the place. And you can disallow some features to talk to other features by enforcing some sparsity pattern in those matrices. Or you can do weight sharing, so then you don't learn all the n by n, say, parameters in the K, but you have maybe a small convolution stencil and you put them in at a regular place. So you can do all these tricks, and you can just write it in the concise language of linear algebra. And of course, now we say data scientist is the sexiest job of the 21st century, but I actually want to say that applied math is also still a good job. Here, this is actually a nice paper, or like a report, which is basically about this neural ODE. Which came about, I think, a year or two ago. After, I think also we did some work prior building up to that. But definitely the idea is that we have kind of got some traction in the machine learning community. Okay, so one example, since I've shown one example in classification, so my view on these deep neural networks is relatively naive. So I have some training data, and I'm limiting myself to very simple, say, classifier, like a linear classifier, or if you do regression, I limit myself to a linear model. Not all data sets in the world you can deal with a linear model. So the idea of the neural network is to propagate features, to basically push them around into some latent space, so that in this case they can be linearly separated, and then you can the way to kind of classify your image, or your image of your points, is you take a point, you find out where it gets propagated to, which color it has, and then you put in that color into that pixel. Okay, so it's a kind of like a two-player game in some sense. That's how I like viewing the problem. So you have some weights associated with the classifier, and you have some weights, these thetas, associated with that transformation process, which is a deep neural network. You can, if you like, lump the W into the neural network. Then it's kind of the last layer, fully connected layer, for example, with no nonlinearity. You can do that too. It's just actually for one reason that will become apparent later. I like singling that guy out. Actually, if you eyeball this, then you can see that in the W there is some hope that this loss function here can be convex in the W. So kind of from an optimization point of view, sometimes it helps if you divide all your variables into the ones that are convex and the ones that you don't know anything about. So these are just notations that I like using here. Anyway, a big breakthrough for us was this ResNet, a residual neural network. It's a really popular model these days in machine learning. So here you have a specific type of forward propagation where on the right-hand side of things you have this yj plus. It's called a skip connection, which basically means that you're learning only the update. So these k's and b's are again unknown. So you want to kind of learn these updates or the residual between yj plus 1 and yj. Okay, and that is, has been found empirically to stabilize things. It's actually a very successful architecture that is crushing many of these competitions out there. So the big breakthrough came when we kind of put an h in here, and we said, okay, that was clearly missing in the original paper, because then you can take a yj to the other side, divide by h, and see that there's a differential equation hidden here. So you can think about ResNet as being a discrete version of a differential equation, which means that you can play movies like this one, which may even play, may not play. I can make it play though. So you can play movies that demonstrate what happens in a trained ResNet, how the trained ResNet goes from this configuration to something that you can classify. So each frame in the video here that I'm showing is basically a layer in your ResNet. It's a hidden layer. And you can see that in the end, toward the end of the day, you kind of reach this separable structure here. And it's a smooth process because we built this ResNet. It's very different from a standard neural network where you don't have this skip connection. Basically, the features can change really drastically from layer to layer, which can be good, because maybe you can have more complex transformations more quickly, but it can also actually really be a pain if you have many layers and you don't have a good way to initialize weights. Here, everything is based on differential equations, so it tends to be easier. Okay, so that is at least one of my central areas of interest are these architectures that you can phrase as differential equations, and we have done some things in terms of stability analysis, numerical methods, of course, extensions to PDEs when you have images, but those are were already covered in my other two talks. So relating differential equations and ODEs or PDEs is we're not the only ones doing it. We were among the first, together with Wine and A, that got then picked up by the neural ODE paper also. And there are a few bunch of different areas that people are looking into this area. So one is modeling DNNs as dynamical systems. Then there's some work on time integrators that I will kind of briefly discuss also. Some more optimal control papers, and I want to highlight this paper, which is a paper that actually inspired some of the experiments that I'm showing. So this paper is Anode. It's basically, if you read the neural ODE paper with a numerical analysis focus, you will see that a few things there don't seem to match what you learn in an undergraduate class on numerical ODEs. Let's say like this. And that paper nicely kind of exposes these challenges as well, and I'm going to expose a few other challenges here in my talk. And yeah, we also have some extensions to PDEs. Okay, so let me just make this a provocative question of the talk, and of course a rhetorical question. So this is more or less, if I look also how practitioners look at machine learning. They oftentimes don't see too much that there are problems still in machine learning. They seem it's a perfectly legit machine that is working. And the typical algorithm is, so we have backpropagation, we have a GPU, we take one of these. We can implement almost anything in those frameworks these days. They become really easy to use. There are tutorials for almost anything. So, I mean, that's clearly a success machine. It's a paper machine. It's making everything work. So why even bother about numerical analysis? Because more or less for every model that I write down, I mean, I can get a gradient, and I can take in like a random batch, and I can take a negative step into that direction and hope to learn something. Okay? So I want to, that's my main motivation of the case studies. So looking under the hood oftentimes, not always, but oftentimes pays off. So here's an example. I think those of us who are teaching will probably face this challenge at one point. So I thought, why not face it today? So if you look at this function here, that's a perfectly differentiable function. If you are an automatic, if you are in an AD setting. So I wrote down a small piece of code here in Julia actually. So, but we can read it probably in any language, because I was just curious, like what would an AD do to this function? So you have x at 0, you evaluate your f, you backpropagate, and then you take a gradient. Okay. Well, so who wants to have a step? Like what would the AD tool give me as a value? Or will it give me a value? Will it give me a warning, an error? Or what is supposed to happen?
0.
0 would actually be my guess. That would be kind of cool, because then maybe there's a hope that we would actually find a stationary point where there is none. No, it gives 1 by any chance. But I think everyone would say like any number between -1 and 1 would probably you could make an argument that this is a good number. So anyway, I think one enabling technology that is one part of what is nice about machine learning is that automatic differentiation now is abundant, and it's easy to use, and it works for more and more functions in the world. Okay, so at no point did the AD here tell me, hey, buddy, I mean, you're looking at a gradient and a function where there is actually, it's not smooth, okay? So we have to kind of set our minds to, like if we referee papers or if we grade students' homework, that just because the automatic differentiation gives you a derivative doesn't mean that the problem is actually differentiable and that this derivative actually makes any sense. And I mean, of course, it's a perfectly legit thing to do if you know what you're doing, because then you have a subgradient, and we can take a subgradient method and all that kind of stuff. But the convenience of machine learning tools kind of sometimes hides these complexities from us. And we shouldn't always forget them, I guess. So here's one case about reversibility or invertibility. So say I have a neural network. And the neural network takes some point x based on some weights, and it gives me a y. And let's say the dimensionality of the input features matches the dimensionality of the output features. So think about this as a coordinate change, or like maybe I want to explore some low-dimensional structures and want to kind of group the variables into active and inactive, or something like that. So you see those networks sometimes in flows, or normalizing flows, for example, I think is one example where you want to do these coordinate changes from like a Gaussian distribution to an interesting distribution. So in those cases, maybe I want to have something like an inverse of a network, so that if I give it the same y, it gives me back my x. Okay? And now there are maybe two ways to think about how to achieve that. And if we want to stay in the ResNet regime, we can think about a very simple type of a forward propagation. So you have this dynamical system where you have a 10H, and then you have just an affine layer. Those weights are time dependent now. And this input point x would be the initial state, and then you propagate forward, say, up until time 1. Okay, so that would be a ResNet, one way to think about a ResNet in a continuous setting. And then you can discretize that ResNet. Say you use a good time integrator like a fourth order on a Cutter scheme, do many time steps. I'm going to show you the classification problem that I use here as an example in a bit. And you can train everything. And the way, note here, so the right-hand side of the ODE is smooth. It's a 10H. I mean, it doesn't get much smoother than that. The K's and the B's here also don't change too rapidly in time. At least you can smooth them in time if you like. So it's a very benign problem. So if you ask someone to get the inverse, so you are now at y at time 1. I think even in some papers these days it said, okay, what do? You just integrate backward in time. And if things are Lipschitz continuum, some assumptions, maybe this will work. Okay, so we'll find out. And the other idea is to maybe do a little bit more modeling and do something what is known as Hamiltonian neural networks, for example, where you split your variables into y's and z's, and then the y gets updated by the z and this z by the y, but they share the same weights. So that is inspired, for example, if you have like a Hamiltonian system, like one gets the y gets upgraded by the gradient of the Hamiltonian with respect to z, and vice versa. So this network is weird. First of all, it's not a standard ResNet. But if you discretize it, for example, you can make it so that the inverse is trivial. Basically, you just reorder all the operations and you go backward in time. So here's how they do. So it's a classification problem with like a 2D feature space, because there I can actually plot the whole data set and the whole image. And I didn't put the ground truth because this is pretty much the ground truth. So the ResNet just eats it alive, and it gives you a very smooth level sets of these functions. You see a few samples here. So all the purple ones I think are in the purple region, and I mean it's hard to find a point that is in the wrong set in this one. And this one did also a good job. I mean, maybe the boundaries are not as smooth as you would want them to be, but I mean they kind of look good. Maybe this one wins over this one a little bit. So now I'm doing an experiment. I've trained the network. Let's do what I proposed. So we take a point here, we propagate it to the latent space, and then we kind of integrate backward in time to hopefully where we started off. That's the plan. Okay? This is what I get in terms of, this plot is a little bit hard to parse. So for each point in the image, in the feature space, I do this experiment. So I go forward and I go backward. I don't add any noise. I try to do as good of a job as I can. And then I compute the norm between my where I started and where I ended up. And I take the log of it just to help you guys see it. And you see the orders of magnitude is basically order 0. There's a lot of yellow stuff in that picture. So the net, what does it mean? I mean, it's maybe a question also that I don't know the answer to. So if you look at the classification results, okay, now I show you two ways to get the job done. That's the job typically you're given. If I also care about the invertibility, this one completely fails me. And I don't even do anything. I mean, I don't even go in the latent space, add some noise, and go back. If you do this, I mean, you will break any network. But this is just, it's an okay time integrator. I mean, it's not like I, just used something that is maybe not even stable or so. It's a state-of-the-art thing. I didn't do adaptive time integration. Okay, well, maybe that's a way to go about this. But you can easily run into trouble here. Whereas with this one, I mean, since it was, I mean, to be honest, it's set up here because it's made to be invertible. You can take this discretization here, you can rearrange it, and it's perfectly reversible algebraically, and it's also stable forward, backward, so you have no error here. Yeah?
Yes, I guess you just said it's stable. So if you did propagate forward the Hamiltonian one and add noise and go back,
you see errors. So I,
that noise that you added?
A little bit bigger. I mean, actually, I did that, and I think I added like 0.1% of noise, and I had a percent noise in total on the back propagation. So it's not like perfectly volume preserving. It's actually a little bit too forward stable. So forward, you lose a little bit of energy. So then on the way back, you increase it. But here, I think overall the relative error was about 30% to start with. So but anyway, so that's maybe one lesson here where you think about okay, I want to do this. If that's what you want to do, use some method that actually allows you and does it. And I should say, there's also has anyone heard of the ResNet, reversible network? It's also based on a similar idea, so that you have two sets of variables, they update each other alternatingly. The idea there is to be to save memory, for example, because you can, on the backward propagation, you can recompute stuff. Those guys are not designed to be backward stable. So, I mean, there are cases, I think I covered that a little bit in one of my talks, where you can easily show that there could be cases where the weights are such that it's reversible in algebra, but it's not reversible in a stable way on a computer.
You showed a video of the ResNet, how the feature evolves through time, or I guess layer. If you look at an analogous thing for this Hamiltonian neural network, do you see a very different kind of?
Yeah.
Because the ResNet kind of folds, right? It has a sharp fold that kind of happens.
Which is tricky though, because it's hidden here. So to get this job done, I go to a 4-dimensional space. So what I do is, I mean, I have a point in 2D. I add 2 zeros. And then I have a ResNet, because the ResNet cannot change its width. It's a limitation of being a differential equation. I mean, you don't go to different spaces. So in that case, plotting videos is very hard and sometimes even misleading. The video that I showed you earlier was a 2D projection. And careful viewers see that something happened that was not supposed to happen, namely particles crossed. I revealed the trick actually in the tutorial talk, where of course you go to 4D space, and then in the video you just show the first 2 dimensions, and that's where weird things can happen. But that's kind of a little bit of the dirty tricks in the business. And so I actually tried this one with 3 channels, and I also got pretty close, but then the video didn't, and the dynamics was very hard to even for me on a computer where I could rotate things around to see. So I didn't want to burden you with that. But yeah, so that's one example. Okay, so then there's a lot of time integrators, and black box time integrators seem to have their moment. And I just want to bring a textbook example back to yeah.
So in the previous case, do you suggest that the Hamiltonian formulation is the best one?
This judgment I don't want to make. I mean, I don't want to say it's the best one, but because I don't know, it's not. That's not what I do. But it's an interesting network. I mean, we found it actually to be very interesting in terms of the prediction accuracies that we get. And on top of that, it has this reversibility property. So we use it, for example, to avoid any memory in the forward propagation. So typically in a deep neural network, when you train them and when you do a gradient descent or stochastic gradient descent, you need to store hidden activations, because that is what the backpropagation or the adjoint solve relies upon. If you are in a Hamiltonian setting, since you are forward and backward stable, it's actually okay to erase the memory as you go and recompute. So it costs you flops, but since you're mostly memory bound in machine learning these days, it actually allows you to have really, really deep networks with limited resources. It's similar to what's written in the neural ODE paper, where it's basically suggested that you don't have to store anything, because in the backward pass you can integrate backward in time. That is one of the big selling points of that paper. I just want to show this picture again. What could happen? And I'm not the only one observing this. So if you look in this Anode paper that I referenced, there's a very simple example where if you actually do this, you integrate forward and backward, you end up in very different places. So it's a well-known thing in numerical analysis that you have, say, a heat equation. You don't want to solve backward in time. So in those cases, you want to use something like this. And there are other options too. So there are also like leapfrog, like staggered discretizations you can use for certain PDEs. But the numerical analysis books have a ton of options for these kind of processes.
There must be some so the fact that the Hamiltonian neural network is so invertible, there must be an expressive power cost that you're paying.
Yeah.
If you apply it to, say, ImageNet or something that it's going to have.
Could be. So far, for most of the problems we have worked on, we can fit them. We can fit the data. But yes, so approximation theory, I don't want to say that there is something to say. And there might be prices you pay. And in this case, I mean, the results did look a little bit worse. If you looked at the boundaries, they were a little bit more edgy. But sometimes maybe it's worth sacrificing the accuracy and having other properties. So it's anyway. So you all know this example. It's kind of a harmonic oscillator. So you have a Hamiltonian actually in a system. So this is a standard example where you can show that if you want to solve this ODE and you just hit it with a very powerful higher order time integrator, yes, in the limit you will solve the problem very well and you will preserve this energy. But if you have only very limited resources, like a few time steps, this may not be the case. So here's an example where so the blue one is basically the unit circle. And if you start on the unit circle, you stay on the unit circle in the ground truth solution. But if you have only a very large time step here, what happens is that even with a good time integrator, you bounce off a little bit. Whereas when you have the labels are wrong, I guess. So the blue one is supposed to be the true solution because that's round. And sorry about that. So the orange one, I know is a valet, and this one is the RK4. So if you look at it, there's a fourth order accurate. This is like first or second order accurate. So it's a worse method in principle, in the limit. But on a certain number of budget time steps, it's actually winning. And if you make the time step smaller, then I mean they all get closer. But still, if you are limited, say you want to have only a very small number of time steps, because that's what your ResNet or your GPU can handle. It's good to think about what preserves the properties that I care about. And if you, for example, there's one paper here about entitled Hamiltonian neural networks. So in there, they have observations from a Hamiltonian system, and they want to discover the physics. Okay. So in those kind of situations, it may make sense, if you know that you are after Hamiltonian, to use some integrator that also captures Hamiltonians. Because with an RK4, you need to invest a lot of time to preserve the Hamiltonian that you're estimating. And yeah, this example is, of course, inspired by one of my favorite books by Uri Ashar on this topic. It's a very nice hands-on book with all these examples written down. That's just a classic, it's not really a deep learning application. It's a standard thing that we shouldn't forget, that we know. So then, this is a big part of the talk I like talking about. So there is this notion, especially when you have differential equations and neural networks, you need to discretize. This is just this slide. So if you have a minimization problem like so you have a loss here. The loss depends on the final time. That's your output features. and you have a constraint that's given by a differential equation. Okay. PyTorch doesn't know differential equations very well. You need to do something at some point. There are two schools. So one is called first-differentiate and then discretize. So what you do is you stay into the continuous space as long as possible. There is something called Euler-Lagrange equations or an adjoint equation. Typically the way that goes is, I promise not to do too much math. So the ODE here goes forward in time. And then based on the whole trajectory, you solve another ODE backward in time. That's called the adjoint equation. And it's similar to backpropagation. Backpropagation actually is a specific case that you run into with those kind of discrete ODEs. But basically what you can do is you can derive this adjoint equation as a differential equation. So you have a forward and a backward, and the backward gives you the gradient. And then you are really, what people like is you're really flexible because you can pick a nice ODE solver for the forward. And then you can study, look at what is the type of the adjoint equation, and you pick the best solver you can find for the adjoint. And they don't have to be the same. The time steps can be different. Oftentimes the adjoint, because it's linearized, it's easier to solve than the forward. So this is a lot of flexibility that people like, especially when you have difficult PDEs, when you have, say, shocks or something like this to worry about. It's very powerful. However, and that's something I want to expose to you, because I've mentioned it to a few people here over the last few weeks, the gradient you get out of the adjoint is only useful if you solve both the forward and the adjoint equation well. So in the continuous limit, you get the gradient. But we don't go to the continuous limit. So the quality of the gradient is going to depend on how well you solve. Whereas in the other way of thinking about the problem, you first discretize this ODE. So now you have a discrete object. We all know what to do. There's automatic differentiation. We can get a gradient out. Okay? That's the other way of thinking about it. So then the gradients that you get, if you actually write down what backpropagation does for you, is oftentimes something like a discretization of the adjoint equation, but it may not be the one that people would recommend you use. Okay? For simple PDEs, it's actually exactly a good discretization, like a heat equation is a standard case. But sometimes this can be a delicate argument to have. However, the gradient is always useful, even if you solve the PDE only very inaccurately, because you literally just algebraically take the gradient. So and this is like an interesting interplay now if you think about fitting data, like we do in machine learning. The data comes with errors most of the time. If I'm looking at the solution of the ODE and I fit that to my observation C, and C has errors, maybe I don't need to solve the PDE or the ODE with a very high accuracy. That's something you do very often in PD parameter estimation. If you have measurements and the measurement has a noise level of 1%, why would you want to solve the PDE with to machine precision? Okay, and this framework allows you to do that. This framework, not so much, because you need to solve it very accurately to get a good gradient out. Okay, and so one thing, I don't know, we have a few people who teach optimization here sometimes, right? No? Katja, you teach optimization, right? Okay, but you do derivative free optimization. I mostly only teach derivative-based optimization. Okay, great. So the first thing that I like to kind of teach my students is when you solve a problem. So here's a problem I took from a paper that is basically a neural ODE implementation in Julia, which I like, and I actually played with their code, and lots of credits and kudos to them. They did a very nice job allowing me to use this example. So you have kind of a differential equation here. This F is a neural network, and you have some observations from a true differential equation. So it's kind of a setup problem in this case. So you actually know what's the right differential equation that generates the data, but you want to express it with a neural network. There are a few of these problems. And the first question when students ask me to help with their optimization problem is, I say, okay, do you have the right gradient? And I say, sure. I mean, I derived it with pen and paper, and then I implemented what I derived. But like with experience, you learn that sometimes what you derive on paper can have maybe a sign error, maybe there's a small factor you're missing or so. Then there's you implement it. So typically, what I ask my students to do is to show me a plot like this. So maybe I can reveal what this plot shows. So what you do is, say you have a function f that you want to differentiate. So we know that f at x plus hd, so it's a small perturbation that I add, is approximately equal to f of x plus the gradient of f of x transpose and then times d and maybe an h in here. Okay? That's what Taylor's theorem says. So now it gives you a way to quantify, and we know actually a little bit more. We know actually that this error here kind of goes down quadratically in h. Okay? So what we can plot is we can plot the error of a Taylor expansion of order 0, no gradient. So that is basically f of x minus f of x plus hd. Okay? As a function of h, I'd expect that to go down linearly in most cases. And you can compare it with h1, which is basically f of x plus, we'll copy this expression. Okay? So that's the error between the prediction given by the first order Taylor to actually what you observe. Okay, and then we can look at the plot again here. So in blue you see E0, and in red you see E1. So this is a plot that is, so this is h, and this is the errors, and it's log-log. So the slope of the red line should be about twice as much as the slope of the blue line. And in this case, so I just took their examples with the default settings. The gradient, I would conclude, seems to be useful. Seems to be about right. If you screw up the gradient, so this is actually a very sensitive test. So you can do this sometimes when you derive a derivative and you multiply it by, say, 0.95, and you will see that this red line overlays the blue line most of the time, because here it's like a little bit tricky to do, because you need to pick this x, which I pick randomly, and I need to pick this d, which I also pick randomly. So every time I run this, I get a different answer. Here actually made everything fixed, but that is, I think, a good plot. So if a student comes to me with this plot, it's fine. So now the question is, so here, if you look at this, so these tolerances, so the knobs I have in a neural ODE, is how well do I solve the time integrator. The time integrator is, for me, it's a black box. It only allows me to tell it the relative absolute tolerance and the absolute tolerance. Who knows what these mean? But they are really, really small. So I actually had to convert. One change I did to the example is to make it run in double precision. Because in single precision, having anything with a tolerance of 10 to the minus 7 didn't seem to be so right to me. So now let's say, okay, now I want to go faster, because this time, this was not a quick plot to run. How can we get faster? We can relax the tolerances. So this is what happens when you relax the tolerances. So I kind of tried to find a sweet spot where we can see some differences in the derivatives. So here, for example, in this region, those lines are parallel. And if we kept increasing the tolerances, we would even have useless gradients, which means that this part here where you have good gradient information is becoming smaller and smaller. And now, I mean, I contrast that with if you just first discretize and then differentiate it, you always see a plot like this. And I made it so that the number of time steps here is chosen so that these ones are equally expensive. And I think this one is a factor of 5 or 10 cheaper than this one. But you always get the right gradient because you basically just use automatic differentiation. So in some sense, it's kind of interesting that in neural ODEs, people actually bother about deriving the adjoints, where there is a perfectly fine way to get it with automatic differentiation. So next thing would be, let's train this thing. So this is only looking at the gradient at a particular point. Let's train these things. And we can actually show what's going on here. So this is the data that is collected. these are the predictions made by the model, and we start them both at the same place. So then we run Adam, of course, and see what happens. And have this as a video. The video is chosen, so the frame rate is the same in both. But if you sit in the front rows, you see the time that it takes to compute the last step. So it's a little bit more here than it's over there. But I chose that by iterates is probably better. So here you can see basically, in this case, you win in terms of the time. You can play it again, actually, because maybe one thing to notice is that this time here changes quite a lot. Goes up and down quite erratically. And I don't have a better way right now to really find out how many time steps everything takes. I can only take a wall clock time between 2 epochs. So this is actually one feature here that you see. And it kind of makes sense because the neural ODE uses an adaptive time integrator. So the number of time steps taken depends kind of on the complexity of the differential equation. And since you are learning the differential equation, the character can be very different. But this was an example, since I only learned about me giving a talk on Monday, I didn't have time to really massage this well. I mean, it was the first thing you implement. It's a few lines of code. Actually, it's easier because you don't need to interface any solvers. And it worked actually out of the box quite well. And then you can think about, OK, let's make it a little bit more of a fair comparison. Actually, it's played already. So that is what happens when you have the worst gradient, but cheaper computation. Guess what? The results do not improve. You don't get really to where you need to be at in this case. So that was kind of interesting. It was a good reason for me to kind of play with these things. So they have been known in the optimal control community for quite a while. But in machine learning, this message has, despite this nice anode paper, has not really been picked up too much. So if you first discretize and then differentiate, it's actually more natural in a machine learning setting. And you kind of have more guarantees about your optimization here. So this slide I put for Katja. Because there's not a free lunch all the time. So in discretize optimize, if you screw up your time discretization, you are actually paying. So this is a cooked up example where I generated some data for this specific kernel that made things explode quite easily, so that I can show you. And I made the data here with a very large number of time steps. And then I can look at the objective function around when I use fewer time steps. And if I push it too far, you see loss functions that come out like this. So you see a lot of oscillations here. And this is the red dot marks the true solution. And in here, it's probably not even a local minimum. So in this case, it's probably, we have to revert to derivative-free optimization methods because sometimes the gradient may not be too reliable. However, it's an artifact of my poor choice of the time integrator. So, but that's a risk in discretize optimize. So I want to put that out because with neural ODEs, the nice thing is, I pick a tolerance, and then I live with whatever computational costs arise from that. Here, one needs to take a little bit more care. And yeah, so if you do this for different test points, those images are supposed to be the same because one is training data, one is test data. They sometimes don't, but you want to use some stability here. And then, finally, so this is really the last example that I have is conditioning. How bad is this machine learning problem sometimes conditioned? And here I made an example that I actually ran into just a few weeks ago. It's a regression problem. And so you are given some data C and some inputs Y, and you want to fit neural network to make that magic happen, to kind of learn the relation between Y and C. And it was, I don't know, this was before Patrick's talk. So Patrick gave a very nice talk about how to feature engineer and how to normalize everything and so on. It was just before that, so I didn't have a good idea how to process this data. And it happened to be a very, very ill-posed or very, very bad data set that I was working on. Which made it interesting from an optimization point of view. So because it actually pushed me to look into a few things that we don't typically look at. So Anyway, what I have here is just a simple, like a single layer network. So you have a sigma ky, and then you have this w outside. So you only have these two blocks of variable. I think in practice I also had a bias, but I removed it for now. And then if you look at this, this is a nonlinear regression problem. If I want to set it up, I can choose the number of rows in K. I can choose. That's kind of the width of the network. Okay, but everything else otherwise is fixed because the y's have a certain dimension and the c's have a certain dimension. Okay. And if I look at this, it's what kind of category this falls into is a nonlinear least squares problem. And it's smooth if I pick a smooth activation function. So for nonlinear least squares problems, the first thing typically we will do in a numerical methods class is to find the Jacobian. So we linearize the residual around the current K and W. And this leads to some formula here. I don't know, for people who are used to this, this is a Kronecker product here. It's like a tensor product. You can basically work this out. To end up here, I had to do something, namely to vectorize the weights in the W and the K. Okay? Anyway, so this is how these look like. One thing you can learn, so the Jacobian in the W, that is the last layer, has a block structure because it has a Kronecker product in here. This K here typically is dense in the end because these Kroneckers here don't really overlap and you have this diagonal weighting matrix. Anyway, the reason I derived them is I did something that you don't typically do in machine learning, because typically these Jacobians you don't get into your hands. You only get matrix vector products with backprop.
Sorry, the Jacobian here is the gradient of what?
So the Jacobian here, so I take the residual as a function in W and K, and I compute the Jacobian with respect to W, that's this guy, and the Jacobian with respect to K, that's giving me this guy.
So it's dr, dW, and dr, dk.
Exactly. Yeah, transpose. Yeah, there's always this thing, gradients and Jacobians. So in other words, this I can multiply with something like a K, and I get something like an R, like a linearization. And the gradient is a transpose of this one. Doesn't matter though in the end. I mean, you can do whatever you want. But typically you talk about the Jacobians here because then that's kind of giving you a least squares problem that you solve in each iteration. And the reason I did this exercise really is to look at the conditioning of this thing, because in nonlinear least squares, that's what you would typically do in the age of pre-automatic differentiation. You would look at the Jacobians, look at the sparsity, and look at a few other things. Okay, so what are the properties? So here's a toy example where I show you here just the singular values of the Jacobian. So the whole Jacobian, I think I mentioned that here, I get by stacking the JW and the JK. And then I have it as a matrix. I made it small enough so that I can actually look at singular values. So one way to read this plot here is you can gauge the condition number of the problem. So it's probably around 10 to the 3, so that's not too bad. You can also look at, are there any gaps in the spectrum? No. Okay, maybe good, maybe not so good. At least there's no redundancy. What can you do? And then the next thing I did, so this was for a width of 8, so 8 neurons in the middle, and I started, I think, with 3, and in my example, actually, you had to go from R3 to R1, and via 8 hidden features. So you can do this for 16, and of course, and on 32. And of course, I mean, all the weights here are chosen randomly. So basically, that is used kind of the same initialization I always do when I start training the network. In the first iteration, I looked at what is the spectrum. And you see that quite rapidly, the spectrum gets more smeared out. Not monotonically, so in this example at least, from 16 to 32, the spectrum the condition number did not go up in my case. But one thing you can gauge from here is, so this condition number here is what, like at least 10 to the 7, if you eyeball it. Maybe 10 to the 6, 10 to the 7. So, and there's no obvious gap in the spectrum. So it's not like a rank deficient problem. So in inverse problems where I come from, this would be classified as an ill-posed problem, because you have slowly decaying singular values without a significant gap. So you don't, which means, by the way, if you're not familiar with that, so if you have an ill-conditioned problem that may not bother you, if there's just maybe some singular values around in the order of 1 and 2, and then you have a gap to 10 to the negative 10, then you know what to do. You just cut them off. So it's not just the condition number, it's also about this gap. But here you have to decide kind of, okay, here maybe you cut off the last 2, but then still you have a very conditioned problem. But in this plot, for sure, you have no way to say, okay, here is where is a good point to cut. That's what's making these problems especially hard. And you realize you have to solve a bunch of them at each iteration. And so in this case, I mean, what I would say is like, even for this simple problem, and I don't really have a really good solution for it right now, but it's something that we are looking into based on this motivation. You see that these problems can be ill-posed, really in the classical sense. So you want to talk about some regularization. You can, think about SGD as being some regularization, but maybe I don't want to use SGD because SGD is not typically used for nonlinearly squares problems. And there are reasons why it's not being used so much for some of the problems. So maybe if you design a better regularizer, you can get around SGD, use a faster method. That's kind of one thing that we like exploring. You see that this is a condition number only of the J. So in practice, when you have a Hessian here, at least the Hessian approximation would be J transpose J. So that would crash for sure a single precision arithmetic in my case. So you want to have some smart linear algebra in here. So for example, one thing, I don't know if people are working on this, is preconditioning. It's a big topic. Can we do something here? There's a big push also to half precision. I think it's very fascinating. The new hardware allows you to do much more compute, but with these kind of problems, maybe not so much. And yeah, of course, maybe you can pick a better initialization that actually reduces the condition number. And I think that some of these ideas about also dropout, for example, that's something I played with. If you take a random vector, and it was actually recommended by my friend Uriasha, you take a random vector, like a Gaussian white noise, and you compute the condition number of that matrix transpose itself. It's actually quite big. But if you delete certain entries, then you can do a little bit better. But yeah, there's something to do here. So, yeah?
A quick question about this. So, if it's ill-conditioned, how would that manifest itself in the actual, so let's say you actually trained this with the,
yeah.
How would it manifest itself in terms of?
Well, for sure, what I know is that a gradient-based method, like full batch gradient descent, will not be very happy here.
Okay, so it's going to be unstable? Or?
No, not unstable, just slow.
Just extremely slow,
yeah. Yeah, very, very slow. I mean, if you look at the convergence rate of gradient descent, or steepest descent in this case, it's very, very slow. I mean, it depends basically on the condition number.
Well, what about an adaptive method like ADAM or something like that? Would it kind of work?
Well, I mean, I would say a Newton method, if you can solve this thing, would work. And ADAM has a diagonal approximation of the Hessian. So, if it's a diagonal issue, so which means there's not much correlation between the inputs, sure, ADAM would do probably well. But what are the odds? This would mean that the W and the K are independent. So I don't think that's the case. So but it's not so clear. I mean, like it's just giving.
I think if for extremely high, for neural networks where you have, so for example, some people use 100 million. Like Amazon uses shallow neural networks like that are 100 million in width, right? Mm-hmm. So so you have a large condition number. What do you?
Yeah, I don't know. I mean, but at least it doesn't hurt looking at it.
Yeah.
I mean, again, SGD, you don't see the Hessian. That's the good news. So if you had closed your eyes for the last 10 minutes, you still live in a good world. But this thing exists. I mean, like it's not. It doesn't go away by looking only at small batches. Anyway, so just to wrap up, so I think there is a room for looking into numerical methods in the context of machine learning. So at Emory, actually, together with Eldad at UBC, we have actually created a class titled Numerical Methods for Deep Learning, where we teach all these things in a semester course, and all the stuff is online, like the course notes and some MATLAB codes, and we are he's teaching it right now, and I'm teaching it in the spring. So next time we will have PyTorch and maybe some Julia codes, and we're ramping it up. And it's actually a nice way to connect also applied math students, because I mean most of the applied math students you have in your departments actually are interested in machine learning, but they don't really find things to work on immediately and things to do. So that was one reason why we wanted to create this class, to kind of have that interchange. And also people who have a CS program and they want to end up at Google, Facebook, Amazon, or wherever and use machine learning, doesn't hurt if you use some of the bare bone, at least in our mind, doesn't hurt if you know some of the numerical methods. So if I go back here, why would we still study numerical methods? I think there are a few things. So people talk about transfer learning, but in the wrong way. So I think since deep learning is similar to problems that we know, like optimal control and differential equations, we can do that transfer learning. Like if we know something, learn something about those areas, maybe bring that in there. Efficiency is a big thing. So if you don't build the right model, you will not be able to process the big amount of data that you have out there. And like 3D image classification or video classification, I still want to see a few more talks on how to actually do it in an efficient way. And then, of course, if you do numerical methods, you abstract a little bit from the little gritty details. So it's kind of interesting to do that. Yeah, this is just summary slide. I don't want to take too much of your time. I think there are a lot of challenges we can work on if we want to do some interesting computational math research here. And yeah, with that, thank you guys, and happy to chat much more.